Hello everyone, this is Professor Ma and this is the summary on the sections on extremas on surface. Uh, the things we are going to talk about is how to find extremas on a function z equal to f of xy, the surface of that, the graph. And we're going to, specifically, we're going to find a way to find the extremas using partial derivatives in the interior of the surface, not on the boundaries. So here's a definition of a relative maximum and the absolute maximum. And here are the picture of it. It's just obvious what it says. Notice a relative maximum says the function has to be bigger than everybody else or xy in a circle around in other the point A, B. In other words, if that's a relative maximum, or maybe it's max, in definition, it has to be bigger than or equal to self everybody around the neighborhood, a small neighborhood around it. And that's a definition of a relative extreme. Uh, we might not have a relative extrema. A typical example is this one, and in particular, the domain of these functions it is defined everywhere except on these two lines, x equal to y, x equal to minus 1. What? That's where x equal to 0. It gives that. And in particular, when you plot the numbers in close to this line, you will see the surface z on these two sides. On two of the sides it goes down, and the other two sides it shoots up. So you get these pictures. And in particular, this surface does not have any maximum or minimum. What went wrong? That is because the domain is not restricted. So we have to restrict our domain in order to make sure the things we want to look for, it's in there. The maximum and minimum exist. And what type of domain will cause problem? Uh, Here, for example, here's a bounded domain but not closed. And here is a domain that's closed but not bounded. Let me explain this a little bit. By closed, we mean it includes its border. And this one is not closed because the border is excluded. And what do we mean by bounded? By bounded, we means it sits inside a circle. This one that sits inside any circle. We require our domain to be both closed and bounded, like this. If I have a continuous functions z defined over a closed and bounded domain, this is the existence theorem says, then the minimum and maximum exist. Absolute minimum, maximum. So this is the existence theorem. Okay. And to find maximum minimum extrema, we do two different things for on the closed and bounded domain. What we will do is we find the extrema inside, okay, find the extrema maximum min or interiors or saddle points, any extrema in the interior, and separately, and we look for maximum and minimal on the boundary, that is on the borders of these shapes. And of course, if the shape is very complicated, then there are many, many things to calculate. Each border have a different function you have to calculate their maximum means. Okay, so let's separate this into two different jobs. Let's look at the interior. The interior, to find the extrema in the interior, that's where the partial x and partial y equal to 0, because that's where the tangent plane is going to be horizontal. And these are the pictures, possible pictures where the tangent plane is horizontal, maximum, minimum, or saddle points. And here are slightly different type of saddle points. Okay. And these I shall call a two pass. If I look at these saddle points as the middle point, saddle point as a pass, uh, in walking, in hiking, in a pass is a low point between the mountain. You go over, and then you can go down the other side downhill, and so saddle point is a point for the pass. But this is slightly different saddle point. This is a saddle point where once you reach the point for the pass, there are two different options for the pass to go to two different sites or into two different valleys. So both of these two type of points are saddle points. So you can uh, easily imagine a path which leads to three or four or five different valleys, channels. So there are multiple shape for saddle points. For maximal and minimal, they look like top and bottom. That's it. But for saddle point, there are many different shapes. Okay. But so once we find, if the gradient is zero, we calculate the partial derivative x, partial derivative y equal to zero, then it's going to be one of these things. And then how can we tell what it is, which one it is? Then we have a second derivative test, just like the 265 for regular minimal and maximal curves. We have a second derivative test. Second derivative test is this, you calculate these determinants. D stands for determinant. In other words, this is determinant of little matrix f, x, x, f, y, y, f, x, y. In this case, it's the same as yx. So this is determinant of that little matrix. You calculate that number at the extrema with the del is zero. And if the number is less than zero, you get a saddle point. If the number is bigger than zero, then you have to look at the second derivatives in the x directions or in y. Okay. If you look at the x directions and the partial second derivative of the partial derivative of the partial derivative is bigger than zero, then that means the point must be maximal, because remember in the case where there's y equal to f of x, and f double prime is bigger than zero, where f prime is equal to zero. It's the same thing. That's a characteristics of a maximal. Okay, and the second derivative is less than zero. Sorry. Okay, where the first derivative is zero. Okay, then it's a maximal, and if it's the other way around, it's a minimal. And so below are some examples. Okay, here's a example of a saddle points. You go through the calculation, find out the points, the critical points, and then you do the D test, determinant test. You find out D's negative, and so you conclude that point is a saddle point. And in this case, it's a one pass saddle point. You go down the other side. Here is a extrema where the derivative doesn't exist. Okay, if I go through the calculation for the partial f equal to zero, partial f x equal to zero, partial respect to y equal to zero, I find there's a point doesn't exist. Okay, 0, 0. It doesn't. It's not defined there. Okay, so. Here is the pictures, and that's where we get its corners as maximal or minimal, where we get the partial derivative doesn't exist. So they might be extrema, the one of the extrema. And here then is another example. And to find, let's find the maximum minimum. And the partial, set the partial derivative equal to 0, and then y squared x cubed. You can solve one of them. Then do substitutions. You solve for x. You run out with these numbers for x. Y is x to the third power, so you run out these 3 points as critical points. You find the z values, plug in z. Oh, let's test them. We will test the 0, 0 is a saddle point. And 1, 1, minus 1, minus 1, they both are minimals. Okay. So the center is a saddle point, and on the side, the 2 minimals. So this is what the graph looks like. Okay. So now the minimum here are actually absolute minimum. Okay, you can just imagine the surface keep going up from to the sides, and the two relative minimum are actually absolute, the lowest points on the surface, with 0 in the center, 0, 0, 0 as a path between the 2 minimal points. Now, if I restrict the domain to 2 and minus, in this x between minus 2 to 2, y between minus 2 and 2, so now find the max and min. Well, where is it on this on the picture? On the picture, this is where the domain is. So let me try to draw the domain. So if I draw this line down, this kind of sits over this. Draw this. I'm trying to draw the domain. Okay, so this x, y. So wait, there is another one back there. There's a one and a 0, 0 down the center. So here is the x-axis. Here's the y-axis. And here's x go from minus 2 to 2. Y go from minus 2 to 2. And 0, 0, 0 sits over this. Okay. In other words, what I'm going to do, I'm going to look at the x equal to, I believe, which one did I look at? I believe x equal to 2. So x equal to 2 is these curves. Okay, so I'm going to look at that curve and look at the max and min on that curve. So I set x equal to 2 in the formula. I get a formula between z and y, and I solve for the relative max and min for these. Take the derivative side equal to 0, and I get a point with the derivative 0. Okay, it's at the position is on the boundary x equal to 2, y equal to cube root of 2 at that locations. Okay. And where is it? Well, remember, this is it sits over here. And this is a boundary along x equal to 2. Okay, so in other words, the positions where the minimum on this curve, the dip over there, that's sits over 2 cube root of 2 and whatever z is equal to. Okay, so that's what that calculation gives us. Is what this point is at. And if I plug in the compare the max and min on the line y from y minus 2 to 2, I find out that the relative min, okay, that is these positions where the derivative is slope is 0, its value is 8.4. It's a relative min. You can tell from there, from the graph. On the boundary, along 2, at the boundary where x equal to, at y equal to minus 2 and 2, okay, you plug in y equal to minus 2, and you will get 48. You get these high points. right there. Remember, this is the domain, and this is the point. This is the this sits over the square domain, and this is the x, and this is sits over the corner at the point 2 minus 2, y minus 2. So I'm plugging minus 2, I get 48. I get these points way up there. And if I'm plugging at y equal to positive 2 as on the other side of that thing, then it's only y z is only 16. So this is 48, this is 16, and this is only 8.4 along the line x equal to 2. Okay. It's not right there, right here. So wrong place. That's 8.4. In other words, these are the max and min on the boundary. So I have to look at all four sides. All four sides. The calculation are symmetric. They all come out to be the same, except at different locations along the boundary. And after you do the calculation on the other sides, and you can conclude the maximums are these 2 points, and the absolute minimums are the from the interiors. Okay, so that's that sections. Okay, and have a good day. Bye bye. And